next section is getting us into the the mathematical portion of this chapter. When I say mathematical, I'm not saying we're going to be solving really anything math when we do this, but it was essentially, I don't know if discover's the right word to say, but it was definitely assisted by, or I don't like to use the word proven either, but solidified almost this new idea of the atom. Okay, it involves extremely high levels of calculus and other forms of math, but the good thing is, though, we don't have to do any of that. All right, but before we get into that stuff, I just want to kind of give you an idea about how goofy an electron is. Okay, now I love showing this short video every year because the character, yes, it's a cartoon. The character is very eccentric and very excited to be talking about this. So, and he wears like a superhero outfit. So who knows? I mean, it's still pretty awesome. So listen to this, about a 5-minute video or so.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. and it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
What do you think? Think you want to go study quantum physics at some point in your career? Yeah. Again, besides the fact that I really enjoy the quantum hero guy and his character, just listening to that explanation, and that's really about the simplest form of explaining you could talk about in the quantum arena when you're trying to explain what's going on. But, you know, that's real life stuff where we're having particles behaving like waves, which we've kind of been leading up to this point in our discussions thus far. But solid matter basically separating and reforming. And then you ask yourself, well, what implications does that have for the future? We could take solid matter, split it, reform it back to its original self, and then, you know, be in some other location. Who knows? Who knows? Now, if you've ever seen Ant-Man and the Wasp and all those movies, Marvel movies, they're talking about the quantum realm, okay? And it's kind of along the lines of what they're utilizing to do the stuff that they do in those movies. In fact, I think the next movie coming out for Ant-Man and the Wasp is called Quantum Mania. So do that for homework whenever it comes out. Anyway, here we are with quantum mechanics. Now, Erwin Schrödinger, he's the one who really developed the mathematical treatment into which both the wave and particle nature of matter could be incorporated. And that's what quantum mechanics is. How can we take both types of entities or ideas, put them together to where they make sense. Now, what came out of this is what's called the wave equation. Okay. Now, I found that when you take the square of the wave equation, it gives you what's called a probability density map. These probability density maps are possible locations where an electron has a certain likelihood of being at any given instant in time. And so we look here on this image, as we see that these blue dots, if you will, are kind of the probabilities, okay? Statistical probabilities. And if you notice here, if we look at where all these lines intersect, that's our nucleus. Notice that the density around the nucleus, bless you, is greater, is higher density around the nucleus. as we get further and further away from the nucleus, that probability decreases, because now we're talking about a much larger area. So, yeah, I already kind of described where the region of the highest electron density is in this image, near the nucleus. Okay, now, if you've never heard of Erwin Schrödinger, he came up with a thought experiment around this time. And again, this thought experiment that he's going to have is going to show you just how, even with the highest level thinkers in the field, this notion of quantum mechanics can drive you batty. Okay.
Austrian physicist Erwin Schrödinger is one of the founders of quantum mechanics, but he's most famous for something he never actually did, a thought experiment involving a cat. He imagined taking a cat and placing it in a sealed box with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, what is the state of the cat? Common sense suggests that the cat is either alive or dead, but Schrödinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrödinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory he had helped make and turned to writing about biology. As absurd as it may seem, though, Schrödinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in two states at once, the computer you're using to watch this couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases, and a cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons, one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior, a set of stripes, regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time. A single electron isn't choosing to go left or right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out wave-like orbit. Bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. An electron in a molecule isn't on just atom A or atom B, but A plus B. As you add more atoms, the electrons spread out more, shared between vast numbers of atoms at the same time. The electrons in a solid aren't bound to a particular atom, but shared among all of them, extending over a large range of space. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor, or an insulator, or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials like silicon. Combining different semiconductors in the right way allows us to make transistors on a tiny scale, millions on a single computer chip. Those chips and their spread out electrons power the computer you're using to watch this video. An old joke says that the internet exists to allow the sharing of cat videos. At a very deep level, though, the internet owes its existence to an Austrian physicist and his imaginary cat.
All right, that's enough cartoons for that. So, with the development of quantum mechanics, we now get what's called quantum numbers. And we go back to that wave equation that thankfully, again, we do not have to solve ourselves. But it gives us a set of wave functions, and we call these orbitals, as well as their corresponding energies. Now, each orbital that we're going to be discussing is going to describe a spatial distribution of electron density. And so we have a set of 3 quantum numbers that we're going to discuss. And we're not going to get through them all today, but we'll at least get through maybe 2 or so. So your first quantum number. This is known as your principal quantum number, and it's denoted with the lowercase n. We've seen that lowercase n already in this chapter. And I said to hold on to that because that's what we're going to be using when we start really talking about quantum mechanics. So principal quantum number denoted with n, and this principal quantum number describes the energy level on which the orbital resides. Now, tomorrow, when we kind of get back into this thing, after we've kind of been able to discuss all 3 of these, I'm going to show you how these quantum numbers work, if you will. Essentially, the series of quantum numbers and the information you're given with those quantum numbers is kind of like when you're looking at an address. Okay? We get more specific with the more detailed information we get in terms of the quantum numbers, and that leads us to where our probability of our electron being found is. Now back to your principal quantum number. As n becomes larger, the atom becomes larger. Okay, because if your n is getting larger, that means your energy levels are getting larger or higher in number, and the only way you can do that is by going away from the nucleus. Now, each one of these quantum numbers is going to have a series or values associated with them that you are going to be responsible for knowing. Okay? N can have values greater than or equal to 1. Again, it could be infinity if we really wanted to, but you know, in our realm, we don't really see that. What we're studying, we're not going to see that. But the reason why is because you got to at least have one energy level, because even the smallest atom, the hydrogen atom, is going to have electrons. They got to go somewhere. So you start off with n equals 1 and continue moving forward. The second one, actually, you know what? We're going to, I know we're a few minutes early, but I don't want to stop in the middle of these if I don't have to. So I'm going to actually pause it here today. We'll pick up with this tomorrow. So yeah, and then we're probably going to get started in section 6 as well tomorrow. But we will be, at the end of this week, doing work with principal quantum numbers and assigning them and doing all that kind of fun stuff. So we're going to pause it for the day.